The topic for today's lesson is solving matrix systems using eigenvalues and eigenvectors. So what we want to do is let's look at a problem we did previously. And we looked at last lecture the system u dot equals au, where u was x dot y dot and A was the matrix 2, 1, 1, 2. And we found that there was a solution u1 equaled 1, 1 e to the 3t. Now let's look again to see why this particular solution is a solution. And the idea here is that u1 dot, the derivative of this, is just going to be 1, 1, a vector of constants, times the derivative of e to the 3t. And the derivative of e to the 3t is e to the 3t times 3. And we end up with then 3, 1, 1 e to the 3t. Now what's got to happen is that AU1 has to be the same thing. And AU1 is our matrix 2, 1, 1, 2, multiplying the column vector 1, 1 times e to the 3t. You do the matrix multiplication. 2, 1 dotted with 1, 1, 2 plus 1, 1, 2 dotted with 1, 1, 1 plus 2. We end up with 3, 3 e to the 3t, which you'll notice is 3, 1, 1 e to the 3t. And what we can see up at the top here is that u1 dot is actually 3 times u1. And that's what happened when we multiplied u1 by A. We ended up with 3u1. Now, generally, if u1 were ab e to the kt, which is a more general form of this solution, u1 dot is going to be ab times the derivative of e to the kt, which is k e to the kt, and that's going to be k times the vector u. So u1 dot is going to be k u1. So it must be the case that when we matrix multiply u1, we also get ku1 if we want a solution. And since u1 is ab e to the kt, when you do that matrix multiplication, what you end up with a column vector ab e to the kt. E to the kt is just a scalar, it factors out. So what we need is a times the column vector ab to be k times the column vector ab. Now, definition, let A be an n by n matrix. The non-zero column vector v is an eigenvector of A if AV equals KV for some real number k. K is called an eigenvalue of A, and V is an eigenvector associated with that eigenvalue k. Okay, and in this last problem, 2, 1, 1, 2 times 1, 1 was 3, 1, 1. 3 is an eigenvalue of the matrix A, and 1, 1 is an associated eigenvector. The idea being here, if you take 1, 1, multiply it by the matrix A, you get the eigenvalue times 1, 1. Okay, so more generally, if that's AB, if you get K times AB, K is an eigenvalue, AB is an eigenvector. Okay, now the basic idea we're going to be using here is if you've got an equation u dot equals AU, we want to find an eigenvalue K of A and an associated eigenvector AB. Then U1 is going to be AB e to the kt, which is a solution of the equation since u1 dot will be AB e to the kt times k, which is ku1. And when we do the multiplication by the matrix, AU1 will be A AB e to the kt, and since AB is an eigenvector, this multiplication gives us KAB e to the kt, which is KU1. So we've got a solution. Now, what we need to talk about now is how do you solve A times AB equals KAB for a non-zero column vector AB, and a few ideas are needed before we can talk about how to do this. First, I need to define I, which is 1, 0, 0, 1, and I'm going to call that a 2 by 2 identity matrix. Okay, and an identity matrix has ones on the main diagonal and zeros elsewhere. The property we need for this to work is that 1, 0, 0, 1 times AB is AB, and that's pretty obvious. When you dot that with that, you get A. When you dot that with this, you get B. So if we take our equation, A times the column vector AB is K times the column vector AB, we can rewrite it as A times AB equals Ki times AB, because AB is I times AB. And this is going to let us actually do some algebra. And now what we're going to do is we're going to move this onto the right-hand side. So we get AB minus KIAB, and we've subtracted that from the right-hand side, which you'll notice was a column vector of size 2. You get 0, but you get 0 as the 0 column. And what we've then got is this equation, A minus Ki times this column vector AB is 0, 0. And we want a non-zero solution to this thing. Okay? And that leads us to the next thing we need, which is a nice theorem that connects solutions to this equation with determinants. Okay, so if you've got an n by n matrix, then you can find a solution to this equation, which is really what we've got up here, if and only if the determinant of this matrix B is 0. So what does this mean for our example? Okay, our example is U1 dot equals 2, 1, 1, 2, U1. A minus Ki is 2, 1, 1, 2 minus K times our identity, 1, 0, 0, 1. Now when you do algebra here, what you end up with is 2 minus K, 1, 1, 2 minus K. And our theorem says we can find a solution to this, a non-zero solution, if and only if the determinant is 0. So we calculate the determinant, and it's 2 minus K times 2 minus K minus 1 times 1. That's 4 minus 4K plus K squared minus 1. And when you do a little algebra, that's K squared minus 4K plus 3. And this particular equation should look familiar. It's the characteristic polynomial we saw for this system in the last lesson, okay? And that's what we call it here, okay? This particular determinant in the indeterminate K is called the characteristic polynomial. And since we need the determinant to be 0, we've got K squared minus 4K plus 3 equals 0. K minus 3 times K minus 1 equals 0. And that gives us 1 and 3. And those are the eigenvalues. Those are the values of K for which we're going to be able to find non-zero columns that solve the system. We're going to be able to find, in other words, we're going to be able to find a non-zero eigenvector associated with 1, and we're going to be able to find a non-zero eigenvector associated with 3. We still need to find those associated eigenvectors. So we want to find V equals column vector AB, which is a non-zero solution to A minus KIV equals 0 for each eigenvalue. So the system we want to look at is 2 minus k, 1, 1, 2 minus k, ab equals 0, 0. And the augmented matrix is going to look like 2 minus k, 1, 1, 2 minus k for the coefficients, and 0, 0 in the column. Now, when the constant column is all zeros, any row operation that you do is going to leave those values still all zeros. So the constant column isn't going to change. It's always going to be all zeros. So most of the time we just omit it, remembering that when we finally solve the equations that it's equal 0. Okay, so let's look at what happens when k equals 1. So when you put in k equals 1, you get 2 minus 1 or 1, 2 minus 1 or 1. So for k equals 1, your matrix is 1, 1, 1, 1, where that's the A column, that's the B column. Row reduction here is really pretty easy. Okay, you take the first row and you subtract it from the second row, and you're done. This thing is in reduced row echelon form, okay, leading 1, zeros, and we notice that B is a free column. Okay, so that means that B is going to be the free parameter t. This equation right here reads A plus B equals, and remember there's a 0 here. Okay, and now that means that A is minus B, which is minus t. Okay, so our solution looks like A, which was minus t, B, which was t, which is just t times minus 1, 1. And here is our non-zero eigenvector for any value of t other than 0. Okay, and we get an eigenvector. One eigenvector is pretty much as good as another, so we can use any one we want. For simplicity, I'm just going to choose t equals 1, and that gives me an eigenvector of minus 1, 1. And remember, that's associated with the eigenvalue k equals 1. So our solution, u1 equals eigenvector e to the kt, is minus 1, 1, e to the k, which is 1t. And if you look back from our last lesson, we found this solution before. This is actually minus u2 from the previous solution. So, I mean, if I tried to find the eigenvalues in a different order, this would correspond to u1. We found a solution that we knew was there from some of our previous work. Okay, now we want to do k equals 3, the other eigenvalue. So you look at the system we're trying to solve. K is 3 times AB is 0, 0. The matrix of coefficients is now minus 1, 1, 1, 1. Remembering there's a 0 row of constants that we're just not writing down. Now, just because I'm picky about these things, I'm going to switch the rows so that there's now a 1 in the first position. And now you can just add row 1 to row 2, and you get this matrix, which is in reduced row echelon form. And again, the second column, which is the B column, is free. So B is a free parameter t. This equation reads A minus B equals 0. So A is B is t. That means our eigenvector is tt, or t times 1, 1. And as long as t is different from 0, we've got an eigenvector. Might as well make t equals 1, and we'll take our eigenvector as 1, 1, remembering that that corresponds to the eigenvalue 3. So u2 is v times e to the kt. V is 1, 1, k is 3. Here's our second solution. Our general solution is going to be c1u1 plus c2u2, and that gives us c1 minus 1, 1 e to the t plus c2 1, 1 e to the t. The only difference between this solution and the one we found in the previous lesson is in the previous lesson this thing was 1 and that was -1, but you can fix that by just taking C1 to be negative of what it was previously. So this is the same solution we found before. Now there are two things to note. First, the characteristic polynomial in this case had distinct real roots. It's more complicated if there are repeated roots or complex roots, and we'll talk about that in some detail later. Second, this was a 2x2 system. Bigger systems are computationally less pleasant, and we will save discussion of larger systems for next time.